Hello everybody, and this is Narendra Kumar again, and it's a fresh morning here, and I think it's a wonderful way to take up the lesson today. And the lesson is, today what we'll be doing is, we'll be answering the wonder questions that we raised in the previous lesson. We had raised a lot of questions freely and without any barriers, and today we'll try to learn, believe it or not, everything. Can you know everything? Just everything about the world? It is possible, because knowledge is not like a, you add one and then another and make it a whole complicated, burdensome, heavy weight like thing. Knowledge is not like that. Knowledge is very simple if you go to the fundamentals, to the essential concepts. There are certain core concepts. If you grasp that, you can actually get the whole, suddenly you can get the view of the whole world. Man, as contrasted with animals, learns through concepts. He has a conceptual faculty, his reason, by which he reduces the whole world into the palm of his hand. You can know the whole world as a unit, as one small thing. Small is beautiful that way, in that sense. So this whole world can be made small, finite, deep, wondrous, simple and rich. That's what we'll try to attempt today. So there were many wonder questions we raised last time. So we started with the beginning, the Big Bang, and today we'll in essence answer those questions. In one whole lesson, we'll answer all the wonder questions we had raised last time, but only in essentials, in core concepts. So the first question which was asked was the Big Bang, the beginning of the universe, as they say in science. What is the Big Bang? Actually, the Big Bang is only a theory. Of course, many scientists would say that it is final, but if you look at it critically, carefully, there are many unanswered questions in the theory of the Big Bang. So I will give the theory and present the theory as it is, with the caution that there is much more data yet to be brought out. Literally, we are in the dark when it comes to certain questions about the beginning of the universe. So what the theory says, I will present it. And that also with a lot of facts and observations. So long back, when people looked at the heavens, and the scientifically minded always wondered about one thing. Obviously, they wondered about things around us and the heavens. The earth was, they looked at the earth in one way, they looked at the heavens in another way. And when you look at the earth, you see some obvious things which everybody sees, like things falling when left from a height. So when you leave something from a height, it falls. Now the scientifically minded were wondered about that. It's actually a wonder to perceive that and ask a question there. Why do things fall? So people usually say, okay, gravity. Gravity is just a word. When I say why, I should clarify that. Why is actually what? What is really happening? So they looked at the heavens and they looked at the earth, and in a way they united earth and heavens. That was a long, very long process of discovery, and it took a long time, lot of observations. And when they first looked at the heavens, they looked at the stars, the moon, the movements of the moon, the movements of the planets which were moving like that. And they didn't know why it had that retrograde motion. So the planets don't move like that across the sky over a period of year, the whole year. You can see any number of videos on that. It moves like that and comes back and goes like that if you observe the planets. So that was a problem. The retrograde motion, it's called retrograde. The English meaning of the word retrograde is backward. So they wondered about the backward motion of the planets. And of course they charted out the motions of the sun and the earth and all that. So obviously the first conclusion they came to, which was not wrong in a way, was that earth is the center and all the things moved around. And we know that Copernicus, in the later period of history, around 600 years back, he came to the conclusion that it was not the earth which was the center, it was the sun which was the center, and earth was moving. Now, that was a very big turning point. And earth was moving. He explained the retrograde motion. Actually, it's very simple logic that he gave, but very deep, very beautiful logic. If two bodies are moving side by side, and they're going together, and one body is faster than the other body, then this body is faster than this body. Though both of them are moving forward, the person in the first body looking at the other body, which is going slower, perceives that body to be going backward. This is very common. If you're going in a car on the highway very fast and some car is coming behind you, oh, there's a lovely bee here, and if a car is coming behind you, and so the car, when you look at the car behind you, it seems to go backward. It is not actually going backward. So its apparent motion is backward. So if two bodies are going parallel in the same direction and one body is faster than the other, then the second body is perceived by the person in the first body to be going backward. And if, so the simple point which Copernicus made was the sun is at the center and the earth is going like this, and the Mars is going beside the earth, and now you observe earth is going faster, so Mars is going like that. You know, I don't know whether I'm able to make it clear. So the earth is going around, Mars is also going around. And from earth we are seeing Mars, let's say. When there's a point here, the critical point comes here, very simple. When the earth and Mars are side by side, then Mars will seem to go backward, though it's going forward. And when earth and Mars are at opposite ends, then when earth goes forward, Mars seems to go, when earth goes this way, Mars seems to go forward. So when it's side by side, Mars seems to go backward, and when they are at opposite ends, it seems to go forward. So it seems to have this motion. Mars is not moving like that. It looks like that. That is very interesting, and that is very deep and subtle. Observing while you are moving, another moving body gives funny motions. That's all. So that is a very standard topic in our physics textbooks, like you have relative motion. So when you have seen that in trains also, it's very common observation. Everybody has seen that. So we feel we are moving, and when we look at the platform, we are actually stationary. We feel we are moving because the train beside us is moving. And when two trains are going opposite to each other, their velocities add up, because this is going and this also is going. So it seems to go faster than usual. And if they're going side by side, again it happens like how I told you. If they're going at the same speed, the other body would look as if it's stationary. If it's going faster than, and slower, it will perceive the other body in different ways. So the first turning point was that the sun is at the center, and the earth and the planets are all moving around it. And by the time they had charted out the trajectories of planets. And then the next crucial turning point which came was, we have to understand that is, they measured the time period. They measured where all they were, and they divided it by time. Simple. So they charted out, and then with that huge data, very complex, perfect data of Tycho Brahe, Kepler came up with his laws. He found some uniformity. He could put them in an equation. What is an equation? Equation is a uniformity. Suppose I say y is equal to x square, it's an equation. So y and x square are related. You keep any numbers in x, then the numbers in y are related with that relationship. So if y is 1, x is 1, y is 2, if x is 2, then y is 4, and that is a relationship between two variables. That is a standard algebraic equation in mathematics which we study in the school level. So he came out with certain simple mathematical equations which we'll go into detail later on, definitely we'll go into that. But he came up with certain uniformity. He came up with certain laws, and he found out that the earth is a slight ellipse, and he had this law of areas and all that. So Kepler's laws were discovered. At the same time, during that time, we had Galileo, who took an inclined plane and he measured it. Again, the measurement process was very important. So he took an inclined plane and he measured the relationship between the distances covered, I should say, in equal periods of time, and he found another relationship, and he found out the acceleration due to gravity. What is called g, which we have all learnt in school. G is the acceleration due to gravity. So acceleration is covering greater distances with each successive interval, we can say like that, and uniform acceleration is covering uniformly. The velocity is increasing, the velocity is the distance covered in unit time. So it goes faster and faster every moment. It goes faster and faster every moment, and it is called uniform acceleration. So suppose I go in a bike and I uniformly move my hand, my velocity will increase, but it will increase uniformly. So the increase will be equal. So in 1 second, if the increase is from my speedometer is showing 20, in 1 second it will be 22, in another second it will be 24, another second it will be 26. The velocity is increasing, but it is increasing uniformly. And we can simply experience that feeling of uniformly increasing. So it goes like that. This is smoothly increasing. So that uniform acceleration due to gravity came out to be 9.8 meters per second square. And then, of course, it was not as simple as that. There were other discoveries made by Galileo. And one more crucial discovery here was two motions. This two motions is very interesting. A body, if it has two influences, like suppose a body is moving like this and another body is pulled, another person pulls that body, then the body would go in a circle. So it can have very different kinds of motions. If you are going in front of your friend like that and I pull the friend, then the friend would go in a circle. He will neither go that way nor would he come to you. Same thing when I throw something. I throw something, it goes like this. Why does it go like that? It neither goes like that, neither does it get attracted towards the earth fully. The motions get combined. What they understood, which is very common, we have a chapter called vectors where we have mathematized that whole concept, but the mathematics is very simple if you understand the physics there. We can take two motions as two separate motions and simply combine them. So if there are two motions, one this way and one this way, we can combine the motions and the resultant motion will be a result or a combination, what is called vector addition of the two motions. These are the discoveries made. These were the discoveries made, and it was then that Newton came on the scene, and he came up with his three laws that every body remains in its state of rest. First law is every body remains in its state of rest or in uniform motion in a straight line. And that was a new law. If a body is left in space, it keeps on going. Motion is unstoppable, if I can say that. Motion can't stop. If a body is moving, it will go on moving. So on earth we don't experience that, so we find it wondrous. In earth we don't experience that because something is stopping it. When I roll a marble, it will go and go and go, and somewhere it will stop. It's only because of the friction, the roughness, the opposite, what is called force, which is opposing it, and it will go slower and slower, and it will stop. But now let's imagine this is made very smooth, very smooth. So it will go further. Make it smoother, it will go further. Make it smoother and smoother and smoother, and make it absolutely smooth. In space, it will be like that, no friction at all. So it will move, encountering no friction. It will go on moving, it will go on moving, and it will go on moving. It will go on moving forever. That was Newton's insight. Actually, it was Galileo's insight, which Newton formulated as a first law. It is called the law of inertia. The word is very crucial and a very beautiful word. If you like English, it's a very beautiful word. Inertia is a reluctance, a resistance to anything. If I have inertia, then I don't work. So in that way, every body in the universe has inertia. So a body remains in its state of rest. It resists motion. You have to give it a force. Force is a concept to move it. Or if it's already in motion, you have already given a force earlier and it's moving in space where there is no friction, it will go on moving. So as such, in the universe, bodies remain at rest or in uniform motion in a straight line until disturbed by a force. A force is that which accelerates the body. Now the concepts of acceleration and force have become linked. Acceleration is the change in velocity. But why will the velocity change? It doesn't change. So it changes because of some influence. That influence is called force. So force is the influence which changes the velocity. Now you have one body, small mass, big mass. So you give equal force. Force is the influence which changes velocity. But the velocity change, the acceleration for a bigger mass will be less. So if you can already clearly see, force is directly proportional, as they say, directly proportional to mass and directly proportional to acceleration. So more the force, more the acceleration, more the mass, less the acceleration. This is the Newton's second law, F is equal to ma. And remember, we are defining force like that. We have to define it in some way. We can't say force is acceleration. If I say force is acceleration, then I give force to two bodies, different bodies. The heavier body, the greater mass, the body which has greater mass will accelerate less. But I give the same force. So force can't be acceleration. If I give 10 units of force and the acceleration to one mass and the acceleration is, let's say, 5, and I give 10 units of force, same force to a smaller mass, the acceleration will be more. In fact, if the smaller mass is half, the acceleration will be double. Obviously, two variables are here. Two things are varying. Force cannot be defined by acceleration alone. You have to bring in mass. But suppose you say force is defined as mass into acceleration. So you have 1 kg into 1 meters per second per second. So 1 second it increases its velocity by 1 meters per second. So it's meter per second per second. So if there's a velocity of 2 meters per second and in 1 second it goes to 3 meters per second, then the acceleration is 1 meters per second per second. That is the units. We can go into units in further detail. What we need to understand now, the deep insight we have got is force has to be defined as a multiplication, as a product of mass and acceleration. It's a perfect definition of force. So there is force. Now what is gravitational force? And that was the Newton's discovery. And he discovered it by an insight which told him deeply. He got the insight through all the observations. When he looked at it, his genius, over a period of 6 months, he got the insight. As they say, the apple fell on his head, and he realized that the moon is falling because moon is being pulled. As I told you, two motions. So moon is going like this and like this. So moon is falling. It's always falling towards the earth. That moon falling and any object falling is because of the same pull of the earth's gravity, or earth's pull, or the nature of the earth to pull. That was a profound leap that mankind took. The heavens and the earth became at once one. It really blasted my mind when I understood it, rediscovered it, I would say, when I understood that the things falling on the earth, which we take for granted, is the same, that's the influence which makes things fall on earth, is the same, that same influence makes the moon fall on earth. But the moon is at a greater distance, and by that time they had made calculations which will go into further detail. I know I am giving a lot of other further details. We will definitely go into those details. We will have a clear logical understanding. But for now, they had calculated the moon's acceleration. They had calculated the 9.8 meters per second square. They knew the distance to the moon, and and Newton made the simple calculation. He discovered that force is directly proportional to the product of the masses and inversely proportional to the square of the distance. Now, instead of doing it like mathematics, let's do it directly, physically. What does it mean? Force, the gravitational force, if masses are more, force is more. If masses are more, force is more. If the distance is more, force is less, and it reduces as the square of the distance. Here, if you have to arithmetize the equation, suppose the distance is doubled, the force is reduced 4 times, 2 square. If the distance is tripled, the force is reduced 9 times. If the distance is taken as 4 times the previous distance, then 16 times it gets reduced. So it gets reduced like that, it reduces like that. That was the Newton's universal law of gravitation. These are the deep core equations. And one more equation is the law is Newton's third law, that every action has an equal and opposite reaction. So if I pull, I go forward. I push the wall. Why should the wall push me? So the forces come in always in pairs, even in gravitation. This attracts this and this also at the same time, instantly. It's not that this caused that. Forces come in pairs in the same straight line, opposite to each other. So that is the Newton's law of action reaction. We have all read that, but now we have got a deeper understanding, I hope. So that explains the whole universe. That's what Newton said. Does it explain the whole universe? In what way does it explain the whole universe? This is arrived at, okay, but then Newton tested it in terms of explained the tides, explained the sphere, why Earth is a sphere, because everything is attracting everything, Earth is a sphere. Why things are moving, because the Earth is pulling the moon, but the moon had a motion earlier. So the combination, how we send satellites. So many things he was able to explain with respect to gravity, and gravity is a universal law which governs the whole universe. This was the turning point in history when we understood that gravitational is universal. Every mass attracts every other mass. We can forget the equations, we have understood it, we will go into further detail, but what we need to understand is in the universe, by nature, by its nature, it's a fact that every mass in the universe attracts every other mass in the universe. And if the masses are big, then the influence is strong. So gravitation is actually a very weak force, not like electrical force, which we'll see later. Gravitational force is very weak force. That's why the camera is not coming to me, because I have a very small mass. If I put it in the equation, then it will not come. But if I were Earth, I won't be able to record. The whole thing will come to me. Everything sticks to Earth. This requires a huge imagination. It requires quiet and peace to understand. It's not that I have taught you and then you have understood it. It takes some time to understand. But if you keep what I'm telling you in your mind and think about it, wonder about it, you will get what I'm trying to say. There is logic, but it's integrated logic. It connects everything. This is called induction. You're arriving at a law through observations, so it's directly in front of you, but you have to do it in your mind with an imagination, which is the actually our attribute. That's what we have, right? We are human beings. So human beings have that attribute to discover laws. Of course, it requires genius, it requires passion, it requires intense focus. Newton was supposed to be a man who could think and think and think. He would not leave it. He was a stubborn thinker. Probably one of the most stubborn thinkers in the world. He would never leave a problem. He had that innate conviction that he can arrive at something which will give him the answer. That was the extraordinary genius of Newton. That's why Newton is revered the way he is revered. But that is a human quality also. You can actually understand. But because Newton had discovered it, definitely, happily, rediscovery is not that difficult. People like me also can understand it. All of us can understand it. In fact, we have to understand it, not just memorize it. So, every mass attracts every other mass. If every mass attracts every other mass, even a small child will ask, then how can the universe be? If you really think about it freely and freshly, innocently, if every mass is attracting every other mass over a period of time, the whole universe should have been at a point. And that was a puzzle. And Newton was such a simple guy, he said, I don't know the answer. But what I know. That's how science develops. What you know, and then you go further. So it went on. And then one day, they discovered what is called the Doppler Effect. I'll be brief. They discovered that the universe is expanding. Every body is going away from every other body because of Doppler Effect. It is called redshift. When light is going away, its frequency is changing. It happens to sound also. When sound is moving away, its frequency, its pitch changes. So that is how much I will tell you now. But they took the light, and wherever you project receive your light, you will find that there is a red shift towards a red frequency. So they came to understand that the universe is expanding, and then they got the clue as to why maybe the universe is not at a point. It's not at a point simply because it's expanding. That is the theory. If it's expanding, they found out the rate of expansion, and they went backward in time, and they found that the universe is at one point. So gravity did act on the whole masses. This is the part truth of Big Bang. Everything mass has to be at one place, and then there was a big bang. So that is a deep research. It's a topic which fascinates me also. Every once in a while, people come up with new discoveries in the newspapers. But I have a hunch, it's just a personal view, that it will take some time before we achieve that clarity and simplicity by which we know other laws. So that is about the Big Bang. So the universe came into existence, and the first element was formed, hydrogen. It filled the whole universe, and certain places the hydrogen was more, as they say, and because it's more, again because of gravity, it started pulling all the other hydrogen towards itself. Over a long period of time, the whole intense pressure created heat. Pressure is heat. We'll come to heat also. So the heat was created. Whenever there is friction and pressure, there is heat. Huge degrees of heat, around millions of degrees of heat was created in stars, and in that temperature, Now, when you go into nuclear physics, you will understand that hydrogen and hydrogen fuse together with this electrons stripped apart, and they fuse together and they become helium with an enormous release of energy, nuclear energy. So that is actually, they should blast, but you also have that huge gravity pulling it together towards the center. So you have now you have a mass of thing which is being pulled towards the center and which is also blasting. That is what happens in physics. It's called balance. So it balances at a point where the inner force and the outward force is equal, and you have a star. The sun I'm seeing now, that beautiful sun which I can't even see fully, all the hydrogen and the is being converted into helium there, and it's going to go on and on and on. So this, and the puzzle which was solved, the puzzle was, why doesn't the sun cool? There's no concept of cooling there. The hydrogen is continuously getting converted into helium, and the huge heat is being created there, and heat leads to light. It emanates light particles. It comes to earth. It gives life and light to all of us. So star is also, sun is also a star. Sun is a second generation star. We'll come to that. But sun and all these stars, sun is a small star. So obviously anybody will say, okay, hydrogen is getting converted to helium, but at a point hydrogen will be over. Yes, it will be over one day. So when it gets over, then obviously only gravity will be there. But when it comes together, I think there's a whole force which comes together. It will flare up. If it's a big star, it becomes a supernova. If it's a small star, it becomes like a red giant, and it will definitely happen to sun one day. After crores and crores of years, millions of years, the sun will die one day, and it will flare up, and it will become very small. It will become a white dwarf. If the sun is very huge, it will take in light also. Light also is a kind of stuff, is a substance, it's a particle. So it will pull in light also. It becomes a black hole. That is the logic. That is the logic of the whole universe. It seems, when I teach to children, they say, that's it, it's so simple, so beautiful. That is the logic of how stars are formed, and the solar system was formed, the planets were formed, the disk converted into planets, and while forming, they formed the circular motion, the rotation and revolution, and the earth was formed, the earth cooled down, the life was formed. Life came into existence because of the chemical reactions, and life evolved, which we'll see in far greater detail when we learn evolution and mutation. That was discovered by Charles Darwin, and later by all the great biologists who uncovered life. So we are at a stage where we have the earth. This earth became what it is after a long time of what is called differentiation. It cooled and it formed this whole earth. And slowly, 350 crore years back, 3,500 million years back, life came, life evolved. And slowly, a wondrous being came 50,000 years back, and that was you and me, man. So I am the product of this whole universe. I am a stuff, as we keep reading that we are the whole universe, all my elements, my body. I'm not matter, I'm not mind. I'm a combination, integration of both. But man came, and the early man came. Now, there started the history of man. Man was born, and that we'll see the birth of man, and how there was a whole history which has brought us till today. That we'll see in the next lesson. So we are now at the early man stage. I am the early man, and I'm a man, just like any other man. But I don't have any knowledge. I'm going to start my journey. What was the journey of man? That we'll see in the next lesson. Thank you so much. This is Narendra Kumar signing out for now. We'll meet again, and we'll trace the journey of man. And then we'll go deeper into all these concepts in geography and physical science and natural science. That will complete our understanding of everything in the universe. Thank you so much.